Okay, I think we can get started. Welcome, everybody. So we are very happy to have Mel Walters. Today he'll tell us about towards a non-perturbative construction of the Matt.
Sorry, I think my internet cut out for a second. Can you guys hear me now?
Yes.
Okay, all right, great. Sorry about that. Hopefully that's the only time. Okay, great. Thanks, Leonardo. And yeah, thanks for the opportunity to speak. I'm really excited to see all of you, albeit virtually. And it'll be great to get your guys' feedback or thoughts or comments yeah, let's keep this as informal as possible. So please interrupt, especially if like I'm going too fast or if something's unclear. So I'm going to talk today about a paper that came out a few weeks ago that I did with my excellent collaborators, Brian Henning, Hitoshi Murayama, Francesca Riva, and Jed Thompson. And I just wanted to take this opportunity to quickly particularly point out that Brian, who's currently a postdoc at EPFL, and Jed, who's currently a PhD student at Stanford, are both on the job market this year. And I highly encourage you to look closely at their applications. I think they bring a very nice combination of like deep knowledge of field theory and also like a very strong understanding of phenomenology that's, I think, rare to find. So I think, and they're both excellent lab papers. So, oh no, 1 second. Oh, there we go. Okay, there we go. Okay, so today we're going to talk about an observable that needs no introduction that we're all very familiar with, which is the S matrix. But just to kind of put us all on the same footing to start, the S matrix is the probability amplitude for given some in state that you prepare in the infinite past, which I'm going to label by some generic label alpha that refers to, say, like the particles, their quantum numbers prepared in some initial state. The probability of encountering some final state, some out state beta, which we often draw of this. Things come in, stuff happens, and things come out. This is obviously very closely tied to many physical observables, particularly scattering amplitudes at collider experiments like the LHC. And in the very first month or two of a QFT class, you're typically taught how to compute these S matrix elements via perturbation theory. So if you're in a theory that's weakly coupled, we have a Lorentz invariant perturbative expansion, which we can write in terms of Feynman diagrams. And as we go to higher and higher orders, we get more and more complicated loop diagrams. We can evaluate these amplitudes to higher precision. And so the question that we tried to answer in this paper and that I'm going to talk about today is kind of a question that I think we all agree is very important, which is how to compute the S matrix when we do not have this perturbative expansion. So in particular QFTs where we have strong coupling or say large particle number, even if you're in a theory that is weakly coupled, once you look at processes like 2 to n, where n is of order roughly 1 over the coupling, also the perturbative expansion breaks down. And so we would like to understand kind of how to compute the S matrix when we don't have this normal familiar tool of Feynman diagrams. And so the kind of end goal is to be able to compute something like E plus E minus to hadrons. And here we have some various experimental measurements of this. So this is the cross-section, the total cross-section E plus E minus to hadrons normalized by like E plus E minus to muons, I believe, as a function of energy. And the point of this plot, I care about the details, but for today, the whole point of this plot is just that there's a lot of rich structure in this cross-section that is not capturable very clearly by perturbation theory. And we would like to figure out a way to compute something like this from first principles. That's kind of the goal. And so just to give away the whole punchline at the beginning, what I'm going to present today is I'm going to present a recipe, a non-perturbative recipe for directly computing the S matrix. So not placing bounds or something like that, but really directly computing it. And the kind of main ingredient that's going to go into this recipe is we're going to use the spectrum of discrete approximate energy eigenstates of your QFT that you've obtained numerically with some sort of method like Hamiltonian truncation. And if that term isn't familiar, I'll explain it later on, but I'm just imagining I have some numerical recipe for computing the spectrum of eigenstates. And given that, I'm going to tell you how to compute the S matrix. And what's very nice about this formula is that we're going to be able to study not just the S matrix to compute scattering amplitudes for kind of physical energies, but we're really going to be able to probe the full complex plane in the center of mass energy S and be able to study the analytic structure of the S matrix. And so very concretely, I'm going to show you results like this, where we have the total cross-section for 2-to-2 scattering in a very special model, which is the ON model in 3 dimensions, and specifically in the large and limit. And the reason I'm going to focus today on this particular case is where it's actually a model that we can solve analytically. And so we can compare our numeric results to the theoretical predictions. And we see that with very low computational power, so done on a laptop on order seconds, we can get roughly 1% accuracy on these theoretical predictions. But this recipe can be applied to much more general theories, and that's what I find very exciting about it. So good, that's where we're going. How are we going to get there? So first, I'm going to just kind of give a little bit of motivation, but more a review of which is not intended to be comprehensive, of kind of some modern techniques that have been developed in going in this direction of trying to directly compute the S matrix at strong coupling. And then I'm going to present our specific recipe, which is basically going to use the Lippmann-Schwinger, sorry, not Lippmann-Schwinger, the LSC, and I forget all of the names for LSC, I should know this. The LSC reduction formula that we're very familiar from QFT classes, we're going to adapt it to a system kind of at finite volume or a system with like discrete spectra. And then we're going to use this formula. We're going to implement it in the specific example I made reference to of the 3D ON model. And then hopefully I'll have about 10 minutes at the end to talk about future directions, which there are many. And it'd be great to also hear kind of other people's ideas and thoughts on various directions that we could go. I think there's a lot of low-hanging fruit. Good. Okay. So when you say non-perturbative methods or strongly coupled quantum field theory, kind of the first method that pops to mind very frequently is lattice Monte Carlo. And so the kind of crucial feature about this sort of approach is that it's Euclidean and a path integral based approach. And so this is formulated directly in kind of a Euclidean spacetime where time is just treated as another spatial direction. And as a result, lattice methods are kind of not directly tied. They can compute many very nice things like correlation functions or the spectrum of the theory, the spectrum of bound states. But it's very difficult for the lattice to make direct contact with kind of inherently dynamical quantities like the S matrix, things that are inherently Lorentzian. However, there are a lot of nice results from the lattice on studying various aspects of the S matrix. In particular, from a very nice method from Martin Lucier, we can, given the spectrum of states, the spectrum like of energy eigenvalues in finite volume, which the lattice is formulated in finite volume, as you take the large volume limit, you can actually extract information about the scattering phase shift in the elastic regime. So if you're looking at 2-to-2 scattering, this is kind of below the multi-particle threshold. So if you have a Z2 symmetry up to 4M, if you don't, up to like say 3M. This allows you to get some partial information about scattering amplitude, scattering processes in the elastic regime. And there has been some nice work by Bulava, Hansen, and some others that have been trying to extend beyond the elastic regime and to try to compute Euclidean correlation functions from the lattice, and then use that information to extract the scattering amplitude. And in general, because of the fact that you have to kind of analytically continue from Euclidean signature to Lorentzian signature, this faces a very ill-posed inverse problem, which they've been trying to make which there has been some progress on solving, but this is kind of a fundamental barrier that's very difficult to overcome in trying to use the lattice to directly compute scattering. And more generally, I think it's worth stressing that even if we had a way of computing scattering directly from the lattice, this is still limited to quantum field theories that have a lattice formulation that we know how to formulate on a lattice. And there are many examples, in particular chiral gauge theories, which the standard model is one of, that we do not have a lattice formulation for, or other situations where we want to look at, say, finite density or finite temperature that is currently unknown how to study on the lattice. And so because of this, we need some sort of alternative to lattice methods to go forward. And so another approach that is well known to this community, and I'm not going to pretend to be an expert on, so I'll only briefly review, is the S matrix bootstrap. And so in very recent years, there's been kind of a renewed interest in placing non-perturbative constraints on kind of the set of S matrices by requiring analyticity and unitarity and deriving the constraints that these place on kind of the structure of allowed S matrices. And we can even study input some amount of theory dependence by inputting information on kind of the low energy behavior of this theory. So for example, this is a nice plot from a paper from a couple of years ago where they were trying to study the chiral Lagrangian, so trying to study pion scattering. And they can input information on the fact that the low energy behavior matches the chiral Lagrangian and then place bounds on kind of the coefficients in this Lagrangian. However, it's still very difficult for this method to kind of isolate individual QFTs. There's a very rich space of quantum field theories with allowed parameters. And if I want to study a very particular theory with a very particular coupling, it's still very difficult or unknown how to, using these very general S-matrix bootstrap type method to kind of isolate these theories. And so we need a way, while it's very good and very useful that we are deriving these very general bounds, in addition, it would be nice to have a way to study specific S-matrices and to kind of get their full functional behavior. And so another method that has seen kind of renewed interest in the past few years is Hamiltonian truncation. And so this is another method for studying non-perturbative physics. And the basic idea is you take the full infinite dimensional Hilbert space of your quantum field theory, and you don't know how to diagonalize that infinite dimensional Hamiltonian. So what you're going to do instead is you're going to truncate the Hamiltonian or truncate the Hilbert space to a finite dimensional subspace. And so you get this kind of finite dimensional matrix that is just the Hamiltonian evaluated within this subspace. Then you numerically diagonalize that truncated Hamiltonian, and that gives you a discrete spectrum of states that are approximation to the true energy eigenstates of the full QFT. And so this has seen a lot of recent interest and a lot of nice results. For example, here are kind of two results in 2 + 1 phi to the 4th theory, where the spectrum was studied as well as correlation functions. But the question is, how can we obtain the S matrix from the kind of approximate energy eigenstates that we get from Hamiltonian truncation? So we have this kind of nice tool for studying some aspects of non-perturbative physics. And we would like to understand how to, using that data that we get from truncation, how to study the S matrix. And so there's been some nice work in this direction very recently. In 2019, this nice paper studied 2D Ising field theory. So the 2D Ising model deformed by both epsilon and sigma, or a transverse and longitudinal magnetic field. And what they were able to do is they were able to do two things. First, they computed the spectrum numerically from truncation. That's what truncation is best suited to do. And then using the exact same Lucier method that the lattice used, they were able to extract information on the scattering amplitude in the elastic regime. That's these blue parts of the curve down here as a function of the center of mass energy S. And then what they were able to do is to use kind of the constraints of unitarity and analyticity. They were able to analytically continue, given this information on elastic scattering, they were able to analytically continue into the full complex plane. So this is kind of the S plane mapped to a disk. And so the physical regime is on the boundary, and they were able to extrapolate inwards. I mean, it's not the full boundary, it's some portion of the boundary, but given that information, they were able to extrapolate in and get very nice results on the scattering amplitude for arbitrary complex S. Also last year, there was a very nice paper by these three authors that were able to combine truncation with the S matrix bootstrap. And so what they were able to do is they first used truncation to compute the energy eigenstates, and then used these to compute form factors. So these are form factors between the one particle state of various operators. I think they looked at the stress tensor specifically. And then what they were able to do is they were use this input data of what are the form factors in 2D phi to the 4th theory at strong coupling. And they use that as an input to this combined form factor S matrix bootstrap that was developed by Karatiev, Kuhn, and Penedonis 2 years beforehand. And with this input, they were able to derive very, very strict bounds that were theory specific, because they were using a theory specific input, the form factors of 2D phi to the 4th theory. And you can almost not tell the difference between kind of the upper and lower bounds. I forget which color, blue or red, corresponds to upper versus lower. They will provide very, very strict bounds on this is specifically the value of the scattering amplitude at 2m squared, as well as its derivative with respect to S. But then they were also able to compute kind of the full S matrix up in the elastic regime specifically. Sorry, was there a question or no? Okay, I thought I heard. Okay. And so, so this is a very nice result for kind of making more progress towards using truncation combined with analyticity and unitarity to learn information about the non-perturbative scattering. However, it would be nice to be able to just directly compute this. It would be nice to not have to do various roundabout ways where we have to use kind of analyticity or do some sort of analytic continuation or do some sort of bootstrap approach or something like this. It would be nice to be able to directly compute the S matrix. And so it's worth taking a step back and asking, why can't we just do this? What's in our way? And kind of, I mean, there's many answers to this, but kind of, I think at bare bones level, the S matrix is defined as the overlap of asymptotic states. So I have a set of in states, I have a set of out states, and the S matrix is just the overlap between these two sets of states. And most methods that we use for studying non-perturbative quantum field theory are kind of inherently numerical. We do them on a computer, which means we inherently have to discretize our spectrum in some way to be able to work on a computer. And to discretize the spectrum, we have to have some introduction of an IR cutoff, which sets the spacing between our states. And this inherently kind of limits the volume, or we can think of it as putting our system in some sort of finite box or having some sort of finite resolution. And this is in direct conflict with the notion of asymptotic states, of states that are really pulled apart at asymptotic infinity. And so just putting our system in a box, we can't really have a well-defined notion of asymptotic states. And for me personally, kind of the easiest way to see this is from the Lippmann-Schwinger definition of in and out states. And so we have this kind of recursive definition that you might remember from quantum mechanics, where we can define in and out states as in some unperturbed theory. So if we write our Hamiltonian as H naught plus some V plus some interaction potential V, then we take, say, the free state that has the same energy as the state we want to study, and then plus this contribution where we just have, this is very roughly 1, where we have V over E minus H naught, which is roughly V again. And so we have this pole down here, and the only distinction between in and out states is kind of the boundary conditions set by this plus or minus I epsilon. And as soon as we go to a discrete system where we have a discrete spectrum, the eigenvalues of H naught and the eigenvalues of H, which are H naught plus V, are just not going to match. And so we're never going to hit this pole, and we're just never going to see any distinction between in and out states. Whereas if we're in infinite volume and have a continuum, then yes, okay, we can hit this pole, we can have a well-defined distinction between these two. And so I don't know if this is helpful, but for me, this kind of like was able to see very concretely like what the kind of hurdle that's in our way of like trying to compute the S matrix using kind of systems that live in some sort of finite volume that are studied numerically. And so the kind of approach we're going to take is to bypass this obstruction is instead of directly computing the asymptotic states is to use LSZ, which connects kind of these asymptotic states to interpolating fields with the same quantum numbers as those particles. And so it connects S matrix elements, the overlaps between these in and out states, to correlation functions. And so this is, I think, a very familiar equation to all of you of if we look at, say, 2-to-2 scattering, the S matrix, or specifically here, the connected part, I'm going to be sloppy and use this overlap to specifically refer to the connected part of the S matrix. This can be related to just the Fourier transform of a correlation function involving insertions of some interpolating field phi that has the same quantum numbers as my particle. And then the typical version that we see of this, we look at a 4-point function. What I'm going to do is I'm going to choose to look instead at the 2-point function where 2 of the particles are reduced. So we have kind of 2 insertions of phi between the 1 particle states corresponding to particles 1 and 4. And the advantage of doing this is that kind of truncation gives me 1 particle states for free. So 1 particle asymptotic states are trivial to construct. They're the same as just like the normal 1 particle eigenstate. It's only when you look at multi-particle states that you have this subtlety with defining asymptotic states. And so P1 and P4 are just the lowest eigenstates that are given to us by truncation. And then we just need to compute a 2-point function of 2 insertions of phi between these 2. And so our idea is basically, okay, truncation is very good at computing correlators. We get a set of mass eigenstates, approximate energy eigenstates, which I'm going to label by their mass eigenvalue M alpha. So alpha is just labeling kind of which energy eigenstate this is that I get out from diagonalizing my truncated Hamiltonian. And then I can insert these approximate eigenstates into this correlation function evaluate the right-hand side, and get the S matrix. This is kind of the rough idea. However, this immediately encounters a problem. And the problem is that if we look at LSC more carefully, LSC is a very singular thing. What it's doing is it's saying that S matrix or S matrix elements are connected to the residues of poles in correlation functions. So the correlation function on this right-hand side has poles, and specifically those residues correspond to scattering amplitudes. And so LSC is kind of this delicate cancellation where you have these factors of box minus m squared acting on each of the field insertions. And the idea of these box plus m squareds is when we Fourier transform, they're just supposed to turn into p squared minus m squared and vanish on shell. So we're basically multiplying this function that has two poles by two zeros to kind of cancel off the poles and read off the residue. However, when we try to do this via truncation, these box plus m squared terms that are out front, they are exact. It's trivial to set p squared equal to m squared. However, if I try to evaluate this correlation function by inserting an approximate set of eigenstates, by decomposing this into a sum of kind of approximate states, I never create an exact pole. I only will recreate kind of an approximate pole because I'm inserting only approximate states. And so you're multiplying exact zeros times approximate poles, and the expression just naively vanishes. And this is when we first started working on this project, this is exactly the problem we encountered. Let's try to do LSE, let's do it with truncation, and we just trivially get zero. So, however, we can bypass this and slightly modify the LSC reduction formula by using the equations of motion. And so the basic rough idea is the following, is that in the equations of motion, we have box plus m squared phi, the object that we're trying to compute the correlation function of, is related by the equations of motion to the remaining terms set by the interaction potential. So concretely, if I look at, say, phi to the fourth theory, this J would contain a lambda phi cubed term. It's the source, the right-hand side of the equations of motion. And we actually can obtain even though the equation of motion we think is kind of a very classical object, we can actually derive a non-perturbative relationship between correlation functions of box plus m squared phi and this source J via the Dyson-Schwinger equations. And so the Dyson-Schwinger equations morally just say that the equations of motion in correlation functions are satisfied up to contact terms. And so we can derive one particular relationship between this variation of the action with respect to phi, which contains exactly the object we're trying to study, box plus m squared, two copies of box plus m squared acting on phi, to this other object here, which is morally a contact term, which I'll write more explicitly on the next page. But this is the idea. The idea is just kind of use this relationship, which we can derive exactly, move this term, the thing we want, the thing that goes into LSD on the left-hand side, and write everything else on the right-hand side. And so what we get is we get this expression. So we get the object that appears in the LSE formula is equal to a 2-point function of the source J plus a contact term where the two sources are on top of each other. And this J prime, the prime refers to derivatives with respect to the field phi. And so again, in the example of phi to the fourth theory, J prime would just be lambda times phi squared. And so the punchline, I realize this might have been a bit fast, but kind of the punchline is that we can rewrite the LSC formula, where we have the scattering amplitude, the S matrix element on the left-hand side, is equal to the Fourier transform of correlation functions, which are now manifestly smooth on shell. So instead of something that looks like box plus m squared acting on phi, we get just straight up correlation functions of the source that have no exact zeros that need to be canceled, have no poles that we need, that we're trying to read off residues of. Just the Fourier transform of these correlation functions literally is the scattering amplitude on shell. And so the kind of advantage now is we have a version of LSC that we can insert approximate energy eigenstates as intermediate states into and compute the S matrix.
Ayman, can I ask you a question about previous
Absolutely.
slide? So which mass is this? Is this the physical mass or the bare mass?
Good. Yeah, good. You're getting ahead, but you're asking exactly the right question. So the mass that appears here is the physical mass. And this is the mass that I read off from, I diagonalize the Hamiltonian and I read off some mass that is generically not going to match the bare mass that's in the Lagrangian. And so because the equations of motion are formulated in terms of the bare mass, that means that J is going to contain a term that is just the shift between those two guys. So on the right-hand side, you won't just have lambda phi to the fourth, you'll also have a term that is like the physical mass squared minus the bare mass squared times phi. That's a really good question. Okay, so modulo this subtlety that Joao correctly pointed out, let's just kind of understand this formula a bit more like schematically. So for phi to the fourth theory, what is this equation saying? This equation is saying that the scattering amplitude, the thing I'm trying to compute, where I have two incoming states go to two outgoing states, there are two possibilities if I just think about this kind of diagrammatically. Either particles 1 and 2 interact with different phi to the fourth vertices, like the very first vertex that they encounter in a kind of a diagrammatic expansion is a separate vertex, in which case that one particle state gets converted into kind of an insertion of phi cubed or j, or the two particles interact at the same vertex, in which case those two guys convert these two incoming and outgoing particles convert into an insertion of phi squared. And so that's all this is saying. It's just that the S matrix is equal to diagrams where the two particles 2 and 3 interact with different vertices, in which case you get kind of a 2-point function of j, a 2-point function of phi cubed in the example of phi to the fourth theory, or they interact at the same vertex, which is this contact term that gives me a 1-point function of phi squared of j prime in the background of the one particle states. And so we've affectionately named these diagrams the cat and the hat diagram to make them kind of easy to remember. And the youngest member of our collaboration actually came up with a Twitter-friendly shorthand for this expression. But yeah, so just really quickly, just to kind of repeat the answer to Joao's question before, the physical mass that's written in the LSC formula does not generically match the bare mass m naught, and so because of this, J will contain additional terms in phi to the fourth theory, for example, proportional to phi and proportional to the difference of the masses. Great. Now that we have this formula, we now want to decompose this in terms of intermediate energy eigenstates. And so what we do is we take this cat and hat diagrams, and then just for the J prime term, for the hat diagram, it's just a 3-point function. So there's no need to insert intermediate states. This can be computed directly from Hamiltonian truncation output. So P1 and P4 just are the lowest one particle eigenstate. So you just compute the matrix element of J prime. And then for the 2-point function of J, there are two orderings. It's a time ordered correlation function. And so for each of the two orderings, you insert a complete set of states. And so this is the one where the J associated with P2 comes before P3, or the J associated with P2 comes after P3. For those two orderings, you get these two expressions. And so we get this final result where we've inserted a complete set of intermediate states. We compute we need to compute this expression. We just need to compute their matrix elements between the one particle state and these mass eigenstates of J. And then we get this just sum over kind of possible intermediate states. And so morally, these pieces are just kind of the two halves of the cat diagram of the JJ 2-point function. And then this last term, this contact term, just corresponds to the J prime 1-point function. And so, good. What's kind of nice about this formula, one thing that's very nice is that it explicitly reproduces the dispersion relation, representation of the amplitude at fixed u. And the reason it's at fixed u is precisely because we've chosen particles 1 and 4 to correspond to external physical particles. And so what we're doing is we're computing the amplitude for a given choice of P1 and P4 at fixed physical u, because these correspond to physical external states. And so the dispersion relation that you may or may not be familiar with, I know many people in the audience are, but I certainly wasn't very familiar to this prior to this project. Basically, you take the analytic structure of the amplitude of like 2-to-2 scattering, which has branch cuts starting at, say, 4m squared as well as minus u. So this is looking at fixed u and in the S-plane. And we can evaluate the following contour integral. And if we integrate and divide by, we just add an extra pole kind of S prime minus S, then we can basically show that this whole integral needs to add up to 0. So we basically need to have the contribution of the pole needs to exactly match the kind of contribution of these two branch cuts. And so we get this relationship between the amplitude, which came from this pole, and then the integrals of the imaginary part, basically the integrals of the discontinuities along these branch cuts. And so we get kind of this nice simple expression. And then the last remaining piece are subtraction terms, are basically the contribution at infinity, or equivalently, if the amplitude doesn't fall off fast enough, we need to kind of subtract off pieces from the amplitude to derive this dispersion relation to ensure that it vanishes at infinity. And so the punchline is just that this expression here is exactly the same as this expression here. So here we have integral over S of the imaginary part divided by poles. And here we have exactly the kind of discrete truncation version of this, a sum over energies of the kind of the mass energies in S as well as in T. And then that tells us that this last piece J prime just corresponds to the subtraction terms. So kind of this correlation function here are the subtraction terms that we need to kind of remove in order to derive this dispersion relation. And you can kind of manifestly see this. This 3-point function is manifestly just a function of U, and so is finite as you take S to infinity, like doesn't vanish as you take S to infinity. And that means that these, and you can also show that basically this numerator right here is the imaginary part of the amplitude. And that's easy to see just because in this expression, the kind of imaginary part is the only part that's imaginary. It comes from these poles down here, this minus I epsilon. And so the poles are just literally the sum of these times delta functions, which is kind of the discretized version of this branch cut piece right here. Maybe that was a bit fast, but kind of just the punchline is that we get this nice dispersive structure. And the reason it's not fully crossing symmetric, we have manifest S and T crossing symmetry, but we don't have SU crossing. And that's for the same reason of we've picked 1 and 4 to be the special particles that we've pulled out. Okay, good. So just to briefly recap before we get to the application, we wanted to compute the S matrix. We wanted to compute scattering particles 1 and 2 going to 3 and 4. So using LSE, we can first relate this to a correlation function of 2 insertions of phi between P1 and P4. Then using the Schwinger-Dyson equations, we can relate this to correlation functions of the source J, as well as contact terms, which I've suppressed here. And then inserting the kind of approximate eigenstates that we get from truncation, we can reduce this to products of 3-point functions of J, which are easily computable from the truncation data. And the advantage of this recipe is that it's numerically stable. There's no delicate cancellation of poles anymore. And all of the ingredients can all be computed from the output of a method like Hamiltonian truncation. Okay, so I'm going to stop for a second. Are there any questions about the general approach before we go to the example?
I had a question.
Yes.
So on your previous slides, I mean,
further back, or yeah.
Yeah, these dispersion relation.
Yeah.
I mean, I think there's no general rule that these integrals over S prime and T prime should converge without a further subtraction, right? Because the imaginary part of the amplitude can just grow and then, or it doesn't have to go to 0. And so these integrals are not expected to generally converge non-perturbatively.
Good.
So yeah, how do you see that in your discretized version?
Let me think about this. Yeah, I guess what you'd be, okay, so good. So let me think about this. What you would be.
But your
so
derivation was for a specific theory, right?
No, my derivation was very general in the sense that literally all I did was I said I have some J. I guess for this I looked at a scalar theory, and then I just said for general J, I can just insert a complete set of states. And so I guess what Walt is asking is just that, or I think what you're asking is that this sum doesn't necessarily have to converge, which is a bit confusing just from a dumb operational standpoint, in the sense that I'm trying to think of like how you could in principle say the same thing for like a correlation function, like why does the sum over intermediate states converge? Yeah, good. This is a good question.
Isn't this a prelude in general of Hamiltonian truncation? The fact that your observables are dominated by infrared quantities, right? So if this thing diverges, then you're already in setups in which Hamiltonian
Good.
truncation-
Yeah, this is a good question. Yeah, so I'm definitely considering the case where I'm looking at relevant operators, like relevant deformations, or like the case that I'm looking at. And in those cases, I would have thought that the imaginary part should generically fall off at high energies, but maybe that's too fast.
I think in general that's a bit too fast. I'm not sure.
Yeah.
Right, QCD you would say has a relevant or marginally relevant interaction.
Well, for marginally relevant, it's a bit more subtle. Yeah, that's true. Yeah. That's a
I'm
good
not sure,
question.
right? Just because high energy, but forward limit is still strongly coupled, right?
That's true. Yeah, this is a good question. Yeah, I mean, the way you would see, like the way I would see this in mind is I would, to answer your original question, I guess I would just see in practice that the sum over intermediate states diverges. That somehow that I like, but that as I increase truncation and as I increase the cutoff of my theory, like then I would find that this diverges. I'd have to think about what to make of that case or what to do. Yeah, what I should do differently when that. Yeah, okay, this is a good question. I need to think about this.
And so you also seem to just need the finite volume spectrum.
Yeah.
Just as the Lucier method, right?
That's right. Yeah.
So in the elastic regime?
Well, no, not just the spectrum. I also need information about the eigenstates. Like I'm really, but yes, yeah.
Oh, sorry. No, you need the form factors also. You need the J.
Exactly. I need the J form factors in addition to the spectrum. That's right.
I see. Okay.
Good. Any other questions about the general approach?
Yeah, I mean, this Ball's question, yeah, makes me think, is this derivation, you presented it for phi to the 4, and it felt very perturbative that, okay, you replaced phi by the equation of motion. If you're scattering glue balls, you can still do LSC, you can create glue ball with some trace of f square, right? Some gauge invariant.
Exactly, yeah.
But then how do you reduce that using equation of motion? Then you wouldn't that be
yeah, exactly. Yeah. So good. So you're jumping ahead to one of my future direction slides. So exactly. So the kind of what we have derived a formula for is any theory where we have a fundamental field that has the same quantum numbers as the particle that I want to scatter. And you're right that there are many theories that do not fall into this category, namely QCD or Yang-Mills or whatever. So the question is how to generalize this. Now, what you could imagine is that there's some way that you could in principle use, if you have some composite operator like trace of f squared, that you could use the equations of motion of the constituent fields to get a slightly more complicated expression on the right-hand side. But this is something we need to think about. Like, I don't inherently see, maybe it's a good question. It's not obvious to me how directly this is connected to Balt's question in the sense that it's not clear to me that theories that fall into this category of you have a fundamental field like have an imaginary part that must be well behaved in infinity. Maybe that's true though. If somebody knows that, that would be great to know. But that's a good question. Maybe I've secretly assumed some information. It's not obvious to me that I have, but that's a good question. That
because in a way you can see you could. What you're showing, maybe it's a derivation of that, right? Because then
maybe that's true.
You should show that there is a dispersion relation.
Yeah. Maybe that's true. Yeah. Okay. This is a good question. Yeah.
Anyway, thank you.
No, thanks. This is very helpful. Okay. Cool. All right. So now let's quickly go through an example. So I'm specifically going to look in 2 + 1 dimensions, and I'm now going to generalize to the case where I have n fields, phi I, and I'm going to look at the limit where the number of these fields is very large. And so I'm going to consider this very simple theory with a quartic interaction. And as is well known, this theory is actually solvable if I take the limit n goes to infinity at fixed m and fixed lambda. And crucially, it's solvable for any value of both the mass and the coupling. And so this is a strongly coupled theory that I can still solve analytically. And so in particular, if I look at, say, 2-to-2 scattering of this field phi I and phi j, then the scattering amplitude is just computable by summing up chains of loop diagrams. And so I get this kind of nice simple structure for the 2-to-2 scattering amplitude, where I get kind of 3 pieces. It breaks up into this nice 3 pieces, which are just different flavor structures. But the simplifying behavior is that multiplying each of the 3 flavor structures is just a function of a single Mandelstam variable. And so in this case, for this particular combination of indices, we get what we have called in our paper the S flavor amplitude, which is just the sum of kind of bubbles in the S channel. And then you can resum these to get this kind of nice simple expression. And so the punchline is just that this is a theory where we know the answer. And so let's see if our method can reproduce it. And so the method that I'm going to use is known as light cone conformal truncation. And the details, I'm happy to talk about them afterwards, but kind of they're not super important for the purposes today. They're really just a truncation method that we're going to use to study this theory. And so very roughly, the idea behind this particular method is you take the Hilbert space of your theory and you're going to describe it in terms of the UV conformal field theory, which for this particular model is just the free massless n scalars that we have. And then when we parameterize this Hilbert space in terms of a basis of primary operators, and those primary operators are Fourier transformed to momentum space. So we just write down the set of all primary operators, and then our basis is just going to be those operators in momentum space. And so we need to discretize this basis to put it on a computer. And so we're going to do 2 things. First, we're going to, for each operator, we're going to discretize kind of the continuous variable p squared that labels these. They're kind of center of mass energy or invariant mass. And so we're just going to discretize these into bins. Set some UV cutoff and then divide that kind of range into bins. And then we're going to truncate the set of operators. So we're only going to keep operators up to some maximum scaling dimension, delta max. And then lastly, this basis can be defined in any quantization scheme, but we're going to choose to work in light cone quantization. So we're going to define our Hilbert space on slices of fixed, on null slices of fixed light cone time, x plus, which is time plus 1 of the spatial directions. Okay, good. So given this basis, we can construct the Hamiltonian for the ON model, diagonalize it, and then use the prescription to compute the scattering amplitude. To do so, we first need to generalize. This is just a minor thing, minor bookkeeping thing. We'd have to generalize our formula to the case where we have ON. So here we just have generalized this where now we're keeping track of indices, but structurally it's exactly the same. There are 3 pieces. There's this first term where J2 acts before J3. We're going to call this the S kinematics term, just because it's written as a sum of poles in S. And then we have this second term, which corresponds to the case where J3 happens before J2. And this is, we're going to call the T kinematics term because it's written as a sum of poles over T. And then lastly, of course, we have this contact term of J prime. Okay, so now let's go through one of the kind of set of contributions to this formula, this kind of general LSC formula, in a bit of detail, just so that you guys can get a flavor of the kind of structure of this formula. So let's specifically focus on the S flavor part of the amplitude. And so that was the term proportional to delta ij, delta KL. And so we can kind of project onto this by doing a particular contraction of the indices and taking the limit n goes to infinity. And if we do that same thing on our formula, we get kind of just this expression here, where we've contracted the indices for 3 and 4 and the indices for 1 and 2. And what we find is that in the large n limit, there are only 2 sets of states that contribute when I look at this sum over intermediate states. So in principle, I should insert all possible states. At large n, the bulk of these form factors or matrix elements vanish. And so I'm reduced to just kind of 2 contributions. For the S kinematic terms, the only states that have a contribution are 2 particle states, which is unsurprising. This is kind of what I would expect from this diagram, is this is just a sum of a bunch of 2 particle states, a bunch of these loops. And so the 2 particle mass eigenstates are the only ones that contribute in this channel. And then in the T kinematics term, basically just because I've kind of crossed particles 2 and 3, then what we get is the exact same contribution of kind of 2 particle states, dressed by kind of two trivial spectators associated with kind of particle 1 traveling until eventually he hits this interaction vertex, and particle 4 being created from this earlier vertex. And so the kind of punchline here is that we can kind of cleanly see that our formula A reproduces the structure of this amplitude, and B, we can kind of understand its contributions, that this contribution here is actually proportional to a theta function in the light comomentum P minus. You can think of this, I mean, equivalent, like morally equivalent to being a theta function in kind of the energies of particles P1 and P2. Not literally, but it's just the theta function is kind of like, you can think of this being morally analogous to this. And so we get these two contributions, and what they say is just that because these intermediate states are physical, we either get this term, which demands that if this interaction vertex happens before this, then the energy or the light comomentum flowing through this had better be positive, hence this theta function. And if we swap the order, then instead we find that this can only happen if P1 plus P2 is negative. And so this is a very general phenomenon that happens, is that when we decompose these in terms of intermediate states, these various terms are proportional to theta functions, just demanding that the momenta of the intermediate states and energies are physical.
Sorry, Matt, can I ask you a question?
Yes.
So I didn't get, do you impose that the amplitude is dominated by two particle exchange, or do you see from your numerical result that these are the dominant one?
So good. So we don't impose anything. What we do is we first evaluate. So here's what we do. We first evaluate the matrix elements of the ON model, and we see that at large n, all matrix elements that mix particle number vanish. And so we see that, okay, like the structure of the Hamiltonian is such that it factorizes into these individual pieces. And then when you diagonalize those individual pieces and you insert them into the intermediate states, you see that the only ones that have non-vanishing matrix elements at large n are those corresponding to two particles. So I don't know if that answers your question.
Thank you. Yes.
Yeah, I'm just like generically what you would do is you would just insert the states and just see what happens. And it's just that for this particular model, because it has some simplifying structure, we can get a bit of intuition of like what's going on with these various S kinematics and T kinematics terms. Okay, so this piece here coming from the 2-particle and 4-particle intermediate states, they both give the imaginary part of the amplitude. And then this term right here, which is just the contact interaction lambda, gives me the kind of subtraction term, the piece that doesn't fall off as S goes to infinity. We can repeat the same process, the same analysis kind of for the T and U flavor amplitudes. So we can contract indices differently. So contract 1 with 3 and 2 with 4. And we see that because our formula has a manifest ST crossing symmetry, we get exactly the same piece, just with kind of particles 1 and 2, with particles 2 and 3 swapped. And so we see that now the S kinematic term gets contributions from 4 particle states. The T kinematic term gets only contribution from 2 particle states, and then we get the same contact interaction. So this is literally the same as the S flavor amplitude, just with S goes to T. For the U flavor, we actually have kind of slightly more complicated structure, and that's because all of the contributions come only from the J prime term. And for this particular contraction of indices, this J prime term has additional contributions coming from mixing of the 1 particle state with 3 particle states that naively would be suppressed by a 1 over n, but are compensated by basically an extra factor of n coming from kind of this contraction of the indices of J prime. This is a bit fast. I'm happy to talk about this later, but the punchline is just that we can easily see in this particular model how all the various ingredients combine to give you the full amplitude. So now we can look at the results. So that was kind of the structure. So here we just turn the crank, plug in our states to our formula, and compute the resulting, say, S flavor amplitude. And so here I'm showing you the imaginary part and the real part of this S flavor amplitude M of S as a function of the center of mass energy squared S. And so what we see is that, so the kind of magenta pinkish line is the theory prediction, the exact prediction that I wrote a few slides back. And then the black is our truncation results. And so here we get agreement to within roughly a few percent for both the real part and the imaginary part. And one kind of thing that's worth noting is that the imaginary part is 0 up to the 2-particle threshold, which is S of 4m squared. For the real part, this has a non-zero value for unphysical values of S. And if we look at those values, we get incredibly rapid convergence. So what we find is that, and this is very intuitive, like what's happening in our formula? Our formula is defined for arbitrary S. For physical values of S, we keep hitting poles. And so very roughly, those poles are what are contributing to kind of the noise that we see over here, as well as some truncation error and like the location of those poles and things like that. Whereas at unphysical values, the expression still works. It's still a sum of poles, just we're looking all the way over here, far away from the poles. And what we find is we get incredibly high convergence. We get at the sub% level, like by a significant margin. And this is very familiar from, there was a paper by Liam Fitzpatrick, Dennis Karatiev, and Hongbin Chen that looked at correlation functions rather than the scattering amplitude, and found very similar results. That if you look at time-ordered 2-point functions away from kind of physical momentum flow, away from physical S, that you get much more rapid convergence for kind of the same reason of just that you're far away from these poles corresponding to intermediate states. So we can.
But can I ask a question? Sorry, yeah.
Absolutely.
But how do you know, like how do you know how the error goes in the complex plane? How do you bound the error? Because it's very easy to hide a small error in the real region, which blows up in the complex plane. So I'm a bit confused by this.
Okay, good. Maybe, okay, let me show you the next slide, and then you tell me, you can repeat your question. So here we're doing the exact same thing. So what we're looking at is we're looking at the amplitude in the complex plane. And for this particular model, like we know the exact amplitude everywhere in the complex plane. And so this is the residual. This is the difference between the magnitude of the amplitude and then the difference between the phase. And so what we're finding is that everywhere in the complex plane, we have incredibly low error. We're almost exactly reproducing the amplitude, and it's only right near the kind of branch cut in the physical, for physical S, that we have slightly larger error. So I don't know. So your question is, you're asking how more generally do I, yeah, what, just say your question again, or does this help answer your question?
How do you get the error in the complex plane? So you just plug your dispersion relation with the error you have on the real axis, right? And then you just go away from it.
Well, I mean, so sorry. So here I'm measuring the error by comparing to like an exact, like a theory where I know. You're asking, how do I estimate the error more generally? Is that your question?
Yeah.
Yeah, good. So this is a good question. Very roughly what you'd want to see is you'd want to see the following. You'd want to look at, so here's the simplest way to estimate the error, which is not rigorous, but just to get a rough sense is, let's pick a random point, like in the complex plane, like S equals 0, or pick some other, like, complex value of S. And then what you would do is I can evaluate my formula. Like I'm going to make no reference to the real axis. I'm going to just only evaluate my formula at this complex value of S, and increase my truncation, like increase the size of my basis, add more and more states, and see kind of how does the value at this point change as a function of delta max, or as a function of like the size of my basis. And what we find, or what so far we found for this particular model, is that this converges very rapidly, that it rapidly becomes insensitive up to like, a few, to the third decimal place or something like that, to the value of the cutoff, which is an indication that it's largely converged and that we have small error. I don't know if this is answering your question or.
Yeah, I think.
But we can talk about it more after. Yeah, it's a good question. I mean, yeah, I think there's still a lot to be explored in terms of rigorously understanding the rate of convergence at different regions. But in practice, it appears that away from the kind of physical, away from the branch cuts, life is golden, and convergence for the examples that we've looked at so far seem to be very rapid, and that it's only actually in the physical regime that things are worse. But maybe that's this, like, it'd be good to understand if that's a general story, or what features of the theory this is true for, or yeah, I'd like to understand this better.
Can I ask a question about the previous slide?
Yep, absolutely.
not sure. How do you sum this discrete? I would think it's a sum of delta functions. So
Good. Yeah. No. Yeah. You're absolutely right. So I swept a bunch of details under the rug, and I appreciate you keeping me honest. So you're absolutely right. So if I literally plot our expression for the imaginary part, it would be an absolute mess. It would just be a bunch of delta functions. Like it'd be impossible to look at. So what we've done here is, because we have a relatively high density of states, we've basically put in kind of a smearing function. So we've integrated over some window and just had a moving window that smooths this out. So that's what I'm doing, is I'm kind of integrating over small windows and then moving this around to kind of get the imaginary part.
And then
similarly, oh yeah, go ahead.
You use that smooth imaginary part in the dispersion relation to get the real part.
No, not literally. I mean, not literally. We could do that. I mean, I think they'd be roughly the same. What we did here is we just did a separate, like.
Here you evaluate with some epsilon. You're not.
We evaluated, yeah, not literally with some epsilon, but yeah. Let me think. Is this literally equivalent? No, I think I would say that we integrated the. Yeah, I would just say we integrated the real part again, but like over some window is the. Sorry. No, that's the wrong way to say it. That's the wrong way to say it. For the real part. Here it's a sum of delta functions. Here it's a sum of poles. So away from the exact things, this is a smooth function. And so what you see when you just plot this kind of raw is that it follows it with just a bunch of spikes every time you hit not on this side, but it's like smooth within spikes every time you hit a pole. And so what we've done is we've actually put kind of we've done the opposite of what we did here. We basically put an exclusionary window and just said, okay, I'm going to sum over all states except for the ones right at like closest to the point in S I'm looking at. And the logic behind this is that if I look at a pole immediately to the right and immediately to the left, those two guys should cancel. They should just have opposite signs. And so this should do a good job of approximating the real part. So that's what we did for this. That's a good question. Thanks for making me explain that. Good. Okay, good. So I have 2 minutes left. So I just want to kind of really quickly go over various future directions. I mean, there's many more than the ones I'm going to list here, but there's like a lot of, I think, exciting things for us to do going forward. Kind of one of the most obvious, like low-hanging fruit is that here we were able to explore the complex plane, but because we chose particles 1 and 4 to be external states, we were able to only study arbitrary S in the complex plane for fixed physical U. And if we really want to explore kind of the full analytic structure of the amplitude, then what we need to do is we need to have no external states and really look at the 4-point function of phi, which is going to be morally the same as we're going to get a 4-point function of j plus various contact terms like j prime, j double prime, all the various combinations. And so this would be a formula that would be manifestly fully crossing symmetric between ST and U, and would be able to be studied for kind of arbitrary complex Manostem parameters. And kind of a nice conceptual question is it possible to study the full multi-sheeted structure of the amplitude from something like truncation? And so here, what we've been doing is we've been accessing complex S, but only on the physical sheet. Whereas if we look at S and we continue through this branch cut, this 2-particle branch cut here, we can go to the second sheet and higher in the exact continuum theory. And the question is, in truncation, naively, this looks like we've somehow removed all the higher sheets because we've replaced this branch cut with a sum of discrete poles. And so there's kind of no notion of going through this and going to the higher sheets. And so I think it's worth trying to think about, is there some clever way to kind of use truncation data to learn information about higher sheets? Or is there some sense in which we're somehow limited to the physical sheet? And what does that mean? And anyway, this is just very open right now, but I think there's just a lot to be explored. Another obvious thing to do is here we looked at large N to kind of test our method. We wanted to see if it worked. And now we want to use this to compute things we don't know. And so to go to finite N theories. So even N equals 1, so to just study phi to the 4th theory. And just really quickly, I just want to mention that the main complications, which are not conceptual at all, they're just things that have to be included, but I don't think there's any obvious obstruction, is that the field strength renormalization Z out in front of the LSE formula was 1 in the large N ON model. It will not be 1, but this is easily calculable from truncation data. You just have to compute the form factor of phi in between the vacuum and the one particle state, the physical one particle state. So this is easily computable from truncation. Similarly, we'll have a non-zero mass shift, which we did not have in the ON model. And that's just a difference in the bare mass. And so this just means J will have to include this delta m squared phi. But again, delta m squared can just be read off from the data. This is just the difference between the bare mass that went into your Hamiltonian, that's a number you know, and the physical mass m squared, that's a number you extract by looking at the low, by looking at just the mass gap. And it's crucial to include this term because he's basically there to cancel off non-1pi diagrams. So basically, in the two external particles, P2 and P3, we can, in principle, have diagrams that reduce back to one particle. So the dumbest would be just kind of 3 particles form a loop and then close, the kind of sunset looking diagram. And this delta m squared is there to exactly cancel these off and ensure that we just get the amplitude instead of these additional unphysical contributions. And then just say very quickly, because this was already discussed before, an open question is kind of how to generalize this to theories, to scattering of bound states. And maybe this can be phrased in terms of, say, the OPE of like the interaction potential with whatever operator you're using, or to use kind of the equations of motion of constituent fields. But this is something that we need to think about. And then lastly, the kind of obvious like long-term goal is to use this for something like QCD. And so we need to apply truncation to gauge theories. And as many of you have probably heard me say before, there are kind of 2 obvious approaches. The naive one is to start with free quarks and gluons in the UV and then kind of gauge the global symmetry, like add gauge interactions. This has some difficulties, namely that in 3+1 dimensions, which we care about for obvious reasons, this is marginal deformation and is also not a gauge invariant deformation. And so you have to be very careful in your introduction of a regulator and truncation, whereas an alternative route is to start with an interacting fixed point like Banks-Sachs, add mass to the extra matter, and this will flow to the same theory, say QCD. And the advantage of this approach is that mass terms are relevant, so we don't have to deal with any sort of marginality in any dimension, and they are manifestly gauge invariant local operators. So there's no subtlety in using just a normal hard cutoff or truncation. And I want to end kind of on a positive note to say that in the audience, there are many experts or many people who have worked on truncation in many different schemes. And even though in this particular example, we use the method of light cone conformal truncation, there's nothing about the general prescription, this like general formula for getting S matrix amplitudes from truncation data that had to do with working on the light cone. And so many other methods like TCSA or the generalization of TCSA working with massive free theories, or even say like potentially matrix product states, though this is a bit more in its infancy and less known how to use this, but I think there's many methods that can be used to study the S matrix, and I think there's been a lot of nice and exciting results in truncation in various theories in the past few years, and I think that it'd be great if those authors and other people in the audience who are excited and interested in this to try to work on studying scattering. So thank you.
Thank you, Matt. Any other questions?
Matt, sorry, can I bother you again about the error? So why
Yes,
why does
absolutely,
the error,
yes.
why does the error grow with energy? Is it about the energy cutoff that you put in the truncation? How do you, yeah, why does it grow?
Ah, you're talking about this right here. Yeah. So I mean, I would say 2 things. So one, what's happening is, yeah, this is a good question. Let me think about this. I think all that's happening is that as we go to high energies, and if Jed is still in the audience, he can correct me because he's the one who made this plot. But what I think is happening is basically the following: is that as we go to higher energies, we have kind of increased spacing between the energy eigenvalues, like just kind of the scale of the eigenvalues, but then the spacing between them, like basically our resolution is getting poorer as we go to the UV. And so I think these kind of widened bubbles that you're seeing right here are basically just a consequence of this, that as you go to the UV, I mean, there's additional cutoff effects, but I think our cutoff is quite large. compared to this. So I don't think this is exactly a cutoff effect that you're seeing. I think what you're seeing is just that the kind of, yeah, just our resolution, the scale of our resolution, the absolute scale of our resolution in E is getting poorer as we go to higher energies, because our state bias towards the IR. But still, I mean, even this bubble is like, you know, this is 1% error. So it's really only very close to the x-axis. We have like larger error.
But this is also related to Balt's question, like because you have a theory which where the amplitude decays at infinity, right? This ON model.
Yeah,
like,
that's right. Yeah. Oh, that's also
something
true.
that-
Yeah, maybe that's related
that
too.
grows.
Just the absolute size of the amplitude is getting smaller, and so that could also be that, like, if we have some fixed resolution in the amplitude, then as the size of the amplitude gets smaller, our percentage like error gets larger. That could also be. That's a good point. I don't know if that was your point, but that's a good.
Yeah, I think a bit, but also like I mean, just because I mean, if you have a growing amplitude, then it I guess like if your numerics are sensitive to this UV piece, right? If it grows, then yeah. I have no idea how you do this problem for something that grows.
I mean, what you could do. So I mean, the dumbest thing to do, right, would just to be like to. So yeah, good. Here's a naive thought. Like, could I not just write down higher dispersion relations where I just add more suppression, like, you know, that Simone and company, like many people have done for looking at it, like let's add additional powers of S in the
but the way you derived it was from LSZ, which does not have these.
No, that's right. I'm just saying the following. I'm just saying that, like, in principle, I could imagine doing the following. I mean, I'm just thinking, I'm spitballing right now. But like, I could write down a dispersion relation that is like amplitude is integral of the imaginary part weighted by multiple powers of S. And then I could calculate the imaginary part via LSZ. And then this should, in principle, and then like, so I have imaginary part is related to correlation function, then apply equations of motion, insert states. Yeah, this is a good question. Okay, yeah, we could definitely try this. Like, this is a worthwhile thing to try. Yeah, I'm really glad that you and Balt asked these questions. I don't in principle see why that wouldn't work. Now, I don't understand why my derivation assumed something about the large energy behavior, but anyway, this is yeah.
I don't think it assumes. It's just in this constant that you put this subtraction constant is what capturing this.
Yeah. Exactly. Yeah.
You just need to work it out. I don't know how exactly. Yeah, numerically.
Yeah. It's a good question. Yeah.
Can I ask maybe a follow-up? So you showed these plots at some fixed value of the coupling lambda over M.
That's right. Yeah.
Did you explore how the errors change as you vary the coupling?
I mean, so not too much. I mean, like, the short answer is a bit. I mean, what we did, so my intuition for this mostly comes from an earlier paper of mine where we were just looking at correlation functions with varying the coupling. And there we found that it was not too sensitive, that it's only once your coupling really becomes very large compared to the cutoff. And we're nowhere near this right now. Yeah, good. It's a good question. Yeah, I could get back to you in terms of the actual range, but I would say for these values of the coupling, no, it's not very sensitive. And that it's only once the coupling becomes, like I would say, orders of magnitude larger, like a coupling of 100 or something like that. But that's a good question.
I mean, somewhere in coupling, there's a critical point somewhere in coupling space.
No,
right?
no. For this particular theory, no. This is the critical point is just M goes, like, setting M to 0. Like lambda over M of infinity.
Because this M is the
large
physical M. Yeah. Okay.
Exactly. Yeah.
Right.
Because there's no mass for normalization. Yeah,
Yep.
it's literally just dialing M to 0. Yeah.
And
But yes, you're absolutely right. Go ahead, Ben.
These plots aren't in this paper, but certainly for like order 1 variations of coupling around this point. So, you know, you want significantly stronger, significantly weaker. The errors are pretty similar. You know, we didn't do some large systematic analysis of this, but it's not like we picked a particular value of the coupling for which these errors were unusually small. This was pretty typical.
ask a question about your last slide?
Yeah.
So yeah, I
This
agree
slide?
that it would be great to do all of that, but so do you understand correctly that your proposal would work for other Hamiltonian truncations of 5⁴? But for example, if we want to study Ising field theory, we'd already be in trouble because we don't know how to, because the sigma field.
Good. Yeah, good. Yeah.
This is the main obstacle to study other theory.
That's right. Yeah. That's absolutely right. So yeah, using field theory would be a good place to try to understand this, to try to figure out. That's right. So for the bulk of these plots, we know how to do it, but you're right. For this first plot that corresponds to using field theory.
Sorry, what's the question about is that the sigma field is a
Yeah, I think the question is like if I want to look at like I don't know the equations of motion associated with this twist deformation, like associated with the sigma deformation, instead of if I were taking fermions and deforming them by like psi bar size to the fourth, like Grove-Neveau type thing or something like this.
Yeah,
I think this is John's question.
Yeah, that I don't think the particles you're scattering, right? That Barak and she were scattering.
Yeah.
They are not.
They're bound states.
Excitations
So,
of any
exactly,
of any field, right? Bound states.
Okay, thank you.
No. But okay, if you start from just the theory with the sigma deformation, like the integrable theory, then you have a theory of then you have like an integrable theory where you have these bound states. And I thought you could think of the epsilon deformation as kind of a potential between these. And now I don't know if that's easily computable, what the equation of motions are for these kinks. Like you're basically forming, but you're right. No, you're right. It's the same thing. You're forming bound states of kinks. So you would still need some sort of like, no, never mind. It's still not known. Like we would have to figure out how to write down. Yeah, you're right. It's the same as like the pion. Like we need to figure out how to compute this formula for bound states.
Thanks.
I have a question.
Yes.
Yes, I've been worrying about the J function. If I understand it correctly, it contains all the renormalization part of the bare field, right? It should be very long in the J.
Very long in what sense? I mean, like I guess
it will contain a lot of operators like phi to the n because you have the renormalization. Is this true?
No. So all you need, good. No, all you need to worry about.
Or it only contains the renormalizable piece.
It will. So J is just coming from morally, J is just coming from the equations of motion, so it will only contain kind of the renormalizable pieces that you initially had from introducing the from the bare couplings in the Hamiltonian. The only the only reason that we had to worry about like renormalization of the mass was just because in LSZ we weren't writing down box plus the bare mass squared. We were writing box plus the physical mass squared, and so that's the only reason why there's some subtlety on the right hand side. Otherwise, the expressions that appear on the right hand side are just the bare parameters, like the original terms in your Hamiltonian. You don't have to worry about the renormalization of these operators. That's going to all be taken care of by basically the numerically computed physical eigenstates that you're computing the form factors of these operators for, if that makes sense. Maybe I wasn't very clear, but
so in other words, you mean that you use all the bare operators, and the only thing that gets slightly modified is that you use the renormalized mass values because that's where but other than that, everything is bare operators.
That's right. In terms of the structure of J, that's right. Yeah.
Thank you.
Does that answer your question, Zeshwan?
Yeah, but let me try to understand. But for the large ON model, large N, there is no such complication at all.
That's right. Yeah, that's right. Yeah. So to be for truth in advertising, we have not yet done this for a theory where we have more complicated normalization, but the structure of the formula, like, yeah, so yeah, we haven't checked this, but the structure of the formula in terms of the derivation, like all the terms that appear are just the bare parameters. And we didn't have to worry about this distinction really between bare and physical for this particular model.
Okay, so
That's right.
for example, if you just want to work out the 2+1D phi-4 theory, this
Yes.
is not a vector model, but just a phi-4. Then
That's right. Yeah.
I believe that the renormalization problem, it might be a complication, right?
No, I only think it's going to be a complication for kind of one reason. Like, so the only subtlety, and now we're getting really in the weeds, but this is a good question. Like, so yeah, let's be very precise. Let's talk about 2+1 phi to the 4th theory, like you asked.
Mm-hmm.
There, J will literally have the following form. It will contain only two terms. It will contain lambda phi to the 4th, phi cubed, and it will contain this term delta m squared phi, and that's it. It will just contain those two pieces. And delta m squared will be whatever the bare mass is. Usually we just set that to 1 or but whatever value. And then just the numeric value that you get from diagonalizing the Hamiltonian of what the physical mass is. And so that's all the entry points of J will be, is just those two.
Yeah, but
those two pieces. Now go ahead.
Yeah, but your lambda here, it should be the bare lambda. Am I correct?
That's right. That's right. That's correct. Yes.
Yeah, but the bare lambda is something like infinity. Is this true? Or you are taking some quotient of the bare coupling with some other bare coupling?
The bare coupling should be infinity. No, in 3D, the bare coupling is finite. The only subtlety here. Good. Okay, I think you're worried about. Okay, maybe you're saying these are the same, but yeah, good. So there is a subtlety with the fact that the mass is divergent in 3D.
Yes.
Yes. Yeah. Good. Okay. Now, good. Now, all this means is that you're absolutely right. So your bare mass will contain kind of a counter term, which is proportional to the cutoff. Like it's not going to be literally infinity because we're working in a truncation with a finite basis. So yeah, you're right. I will have a cutoff dependent part of delta m squared who is explicitly designed to cancel cutoff dependence that arises from these sorts of diagrams here. So it's still implementable on the computer. Yeah, you're absolutely right. Yeah, delta m squared will, for that sort of theory, be dependent on the cutoff. But the idea, which we should check this, like we should see it explicitly. But the intuition is that, yeah.
Yes. Okay, thanks. This answers my question.
Yeah.
Okay. Well, unless there are other questions, let's thank Matt again, and we'll communicate on Slack about the next seminar. Thank you.
Okay. Thank you so much.